next talk is on simulation equivalent reachability of large linear systems with inputs, and Stanley Bach is going to give the talk.
Thank you. So I'm Stanley Bach. I work for the United States Air Force Research Laboratory, and this is a joint work with Sridhar Dugarla from the University of Connecticut. So before I start, I wanted to give some sort of motivation and inspiration about why CPS verification sort of is important. So the example I want to give is automated ground collision avoidance. So this is called AutoGCAS. It's a sort of a real system that the Air Force has installed on F-16s, and it does sort of what the name says. If there's an aircraft and it's going towards the ground and it's sort of in imminent danger of crashing, the system takes control away from the pilot and issues some sort of recovery maneuver to keep the aircraft from crashing. So the system has sort of been in development in a long time. You've probably seen various iterations of this in research communities for sort of small vehicles or sailboats. But it's only in the last 2 years that the system was deployed on F-16s. And so since it has been deployed, I can show you videos of the system sort of in action. So this is a first-person view of sort of an F-16. This is taken in May 2016, so about 1 year ago. It's a training mission, so this is a student flying an F-16, and there's an instructor in another plane. The sort of important things to pay attention to, so there's this horizontal line here, that's the horizon line. So right now the aircraft is rolled a little bit to the side. These numbers here are the altitude. So starting out, these are two different sensors. He's at about 17,000 feet, which is above 5,000 meters. So let's see what happens as the student does certain maneuvers. So what you saw there was a turn going on, so that he rolled the aircraft sideways and sort of pulled back. And then something sort of bad happened, right? Instead of completing the turn, the aircraft sort of turned upside down, and now it's starting to head towards the ground. So this is an instance of what's called G-lock, or gravity-induced loss of consciousness. So F-16s are very maneuverable aircraft and very fast aircraft. If you're doing a turn and you're going at a very high speed, basically the blood can rush from your head and cause you to pass out. And so this pilot has passed out now, and the aircraft's sort of flying on its own. Furthermore, this was a high-speed turn, so the aircraft was going at sort of full afterburner. So the aircraft's not just heading towards the ground with a passed-out pilot, but it's doing this at full speed. Let's see what happens.
Fuel recover. Fuel recover. Fuel recover. Fuel recover.
So you heard the instructor yelling to the student to recover the aircraft. Of course, he's passed out. He can't do that. The system detected that there's an imminent crash and took over, leveled the aircraft, and pulled up now until you're back above the horizon. So now the system is safe. If you look at the altitude reading, it's about 4,000 feet, or the radar sensor says 3,000 feet, so less than 1,000 meters. So in the matter of a few seconds, the aircraft went from above 5,000 meters down to below 1,000 meters. And so you can imagine if that system wasn't in place and didn't take over within the next second or so, the pilot would be dead, right? And by the way, also the aircraft cost $25 million, so we're happy that was saved as well. And so, yeah, for this crowd, you can imagine how many PhD students you could fund with $25 million. Right? So the Air Force likes this system. It's in place. It wasn't developed using formal methods. It was developed using simulation and testing. And so this is difficult because there's a lot of sort of back and forth that goes in the design of this type of system. So the system can't be pessimistic. If the pilots can't fly very close to the ground, if they can't fly in canyons because the system takes over, they'll disable it, right? So there's a lot of tuning that went into designing the algorithm. And every time you change the algorithm, you have to redo all the simulation and testing that you did before. So the Air Force doesn't just have F-16s, though. We have dozens of different types of aircraft. And so if it were free, this system would be on every aircraft, right? But it's not free. It's very expensive. So verification methods, I hope, can analyze this type of system and then reduce the testing burden when you're designing it, and so therefore reduce the cost and increase deployment. So as a formal verification person, I'm looking at the system, and this is a reachability problem, right? We have a system, we can model it, we have a safety condition that we're trying to avoid, we have some recovery behavior, we should be able to analyze this system. So the good news is it's a very well-studied system. So this is a first-year graduate textbook for aerospace engineers, Stevens and Lewis. There's an appendix in there specifically on F-16 modeling, and this book's been around for 20 years, right? So great, we have a model of the system. The bad news is it's a complicated model, so it has a lot of features that make reachability analysis difficult. But the good news with this is we're researchers, right? So what I see here is a series of challenges that we need to address with the knowledge that if we're successful, we can sort of have these really amazing applications that can make use of our methods. So that's the motivation part. Let's go into the talk itself. So what we're trying to do in this paper is chip away at one of the problems for making reachability methods more applicable. Specifically, we want to address the scaling problem, scalability problem. So we're considering a limited class of systems, linear time invariant systems, x dot equals ax plus bu. So if you took a state-of-the-art reachability tool and you tried to analyze a system, and your system had, let's say, tens to hundreds of dimensions, and you chose the right parameters, you might be successful. But you can't really go much bigger. With the methods we developed in this paper, we can go to over 10,000 dimensions, so 2 orders of magnitude increase in scalability. And sort of another nice thing is we have counterexample generation. When the method says it's unsafe, we generate a counterexample, which is very useful for debugging and checking how accurate the method is. So that was the one slide summary. Before I get into math, I just want to say in general, when you're doing model checking, you want to represent a set of states and how that set of states changes, right? And so that's both in the software case and in the cyber-physical systems case. So cyber-physical systems change according to differential equations. So first I'll describe the way the system changes and then a little bit about how we represent sets of states. So we're considering linear time invariant systems with inputs, and so the nice part about these systems is that you can write down the solution, right? And so there's this input-free part here, and then there's the effects of the inputs here. But we're not just considering single sort of initial sets, single points. We want to consider sets of initial states. So if you have sets of initial states, the situation doesn't change too much. By sets here, for this talk, I mean conjunctions of linear constraints. So your initial state is within one of these sets. Your inputs are within one of these sets, and the inputs, they're changing over time, but they're not changing arbitrarily, so there's some bounds on how they can change. And so the solution looks pretty similar. There's some difficulty here. We have a matrix exponential times a set of states now. We have a Minkowski sum instead of an addition, so I'll show you what this is in a second. And then you have this integral term, which I'll also simplify a little bit later. But if you don't know Minkowski sum, it's essentially the addition of 2 points in a set. So you take a point from set A, a point from set B. If you add them together, that point is in the Minkowski sum. Geometrically, it looks something like this. If you have a square Minkowski sum with a circle, you get sort of this rounded, bloated square. So the way to simplify this sort of nasty integral is to consider that rather than having arbitrary input functions, we consider them to be fixed between time steps. So they can change, but for each time step, they're fixed. What this lets you do is sort of simplify this to just a set of states. And sort of as a note, if you want to consider dense time or inputs that change sort of continuously between time steps, there's known techniques to do that. It essentially just consists of this equation bloated with some extra sets. But I won't go into that in this talk. So that was the single step case where you wanted the set of states after some time t has evolved. So after 2 time steps, after 2t, you have this sort of recursive formula where you take the previous set of states and you apply the matrix exponential, and then you add another Minkowski sum with the input set. So after 2 time steps, you now have the Minkowski sum of 3 sets. After I steps, you have, again, the Minkowski sum of I plus 1 sets, where, again, you have this input-free part, and this is all the effects of inputs. So one sort of optimization you can see that is if you're doing this computation step by step, which you would be for reachability analysis or for safety verification, a lot of these terms are repeated, right? The only thing that changes between time steps is you have a new input free term and you have an extra input effects term. So the extra work you need to do at each step is you can compute those 2 terms, you perform a Minkowski sum, and then if you're doing safety verification, you now check if there's an intersection between this set and your unsafe states. So that was how time is elapsed, how we sort of, what's the transition relationship, in a sense, for systems with ODEs. What's the representation of the sets of states? So for this, we use something called a linear star, and it's a version of a generalized star set, which was presented in CAV in 2016 by my co-author. And so the neat parts of this representation is that it's efficient for time elapse, so matrix multiplication. It's efficient for intersection checking, which essentially becomes linear programming. And sort of what's new in this work is we also show it's efficient for Minkowski sum, which we need to handle inputs. So a generalized star set essentially reduces to a set of linear constraints. This is what the set of linear constraints looks for a system. In this case, it's without inputs. So initially, you're in this set. And you can see that there's constraints on the initial sets corresponding to that. This is the matrix exponential, which shows how the initial sets would evolve after some time elapses. So if you solve this LP, now you'd have if it's feasible, you would get an assignment to xy, which is the point that you've reached, and alpha 1, alpha 2, which is the point where you started out at. That's the counterexample. With inputs, it's a little bit similar. You construct this sort of larger basis matrix, which consists of just putting the basis matrix of the component stars next to each other. And similarly, you'll take their constraints and you put them sort of beneath them in this matrix formulation of linear constraints. And now what happens is, at every point in time, you're adding a new input effects term, which consists of adding some columns to your LP, as well as the constraints on those columns. So this looks bad initially, right? Because this LP is growing quadratically. But LP solvers they use sparse representations, right? So if you look at the number of non-zero entries I'm adding at each step, it's constant. And furthermore, doing it this way, what it allows you to do is actually, you don't have to modify the existing set of linear constraints. When you add a new set of input constraints, you just add new columns and new rows, right? So you can reuse the LP from the previous step, and that's more efficient. So this method, you could imagine now doing reachability or safety verification just using this approach. But it won't scale to 10,000 dimensions. And so there's a couple optimizations you have to do if you want this method to really fly. And so there's this great quote by Ken McMillan about how engineering really matters for these applications. And these are optimizations in a sense, but you really have to do them if you want to analyze these large systems. So using a generalized star set, we have this sort of old optimization, which is that you can efficiently compute e to the AT. And by old, I mean about a year old now, so not too old. The two that I'll cover are these other two optimizations, which is solving the LP in a decomposed fashion and using warm start LP. So if you're optimizing over a set of states, that's a Minkowski sum of sets of states, you have this property, where if you want the maximum over the set of states, then you can just compute the maximum of the component sets and add them together. That's from the definition of Minkowski sum. So what this means is that if your unsafe set of states is a single linear constraint, you never have to compose the full LP. You can just work on the small LPs. If your unsafe set is not a single linear constraint, but a conjunction of linear constraints, you can still use this as sort of a necessary condition. You sort of take the first one and wait till that one can be satisfied before you start working on the full LP. And there's sort of other optimizations we can consider based on the structure of the LP as well. The second optimization is warm start linear programming. And so the way a simplex-based linear programmer works is that it'll find solution at you have this set of linear constraints which defines a polytope, and you start at a vertex of the polytope, and you'll hop from vertex to vertex optimizing a function until you find the optimal one. What happens between iterations of the algorithm is that you'll slightly modify your set of constraints. If you have a very small time step, the reachable set of states only changes very slightly. And so what this means is that, like, if I took this polygon and I, let's say, rotated the lines by 1 degree, very likely this would still be the optimal point for this direction. And so that happens for reachability as well. Basically, usually when you actually do the LP solving, if you're using this warm start optimization, you have 0 iterations of LP to do. You're already at the optimal solution. So we benchmarked this method. We have a tool named Hyla, which is sort of available and you can download. And we looked at a benchmark suite for large linear systems. So this consists of 9 benchmarks, ranging from 11 dimensions to about 11,000 dimensions. And Hyla succeeded on all of the benchmarks. So it was the first tool that was able to do this. I'll look at a couple of them here. The first one is the International Space Station benchmark. So this is a structural model of one of the components of the International Space Station. It's a 271-dimensional system. And what you're trying to check is that the output Y3, which is a linear combination of your state variables, is bounded. So what's interesting about this system is that for most of the benchmarks that were proposed, the specification was safe. But the specification was derived using simulations. So it's possible it missed cases, which is what happened here. So HYLA actually found a counterexample for the system that nobody knew about beforehand. Here's the reachable set of states plotted. So this is the output, this is time. As you can see, the output after about 13.5 seconds exceeds the bound that you're trying to guarantee. HYLA can then, when you solve the LP, you'll get an assignment again to the point that's unsafe, the point that you should start at, and then also all the inputs you should use. So then you can feed that into an external high accuracy simulation to check whether this counterexample is sort of a real counterexample. And that's what's shown here. So really the counterexample, this is the output over time, and it has this really wild oscillatory behavior. And what's sort of more interesting is that if you look at the inputs that you need to apply so that this violation is reached, you need really a very specific set of inputs at very specific points in time to reach this violation. So this is actually the output of HYLA. HYLA will tell you which inputs to use at every point in time. So if you try to do, this is an exhaustive simulation of this system, right? So try every corner and every possibility of inputs at every time step, right? So 270 dimensions have intervals, so there's 2 to the 270 corners of this box. At every point in time, at every time step, you have 8 choices of inputs. There's 3 inputs, so choosing all the combinations gives you 8. And then this is the number of steps you need to do. So the violation is at time 13.71, and we use a time step of 0.005. So that's 3 followed by 2,557 zeros. So a huge number of cases. Simulation will not work on this system. We also tried sort of stochastic simulation tools, and they didn't succeed after about 4 hours. And so HYLA for this system was about 1.5 minutes. We tried the larger system. So this is the 11,000 dimensional system. In about 6.5 hours, we could compute 4,000 steps and sort of verify that the system was safe. When we strengthened the specification, we could then get a counterexample, and the relative error of the counterexample versus the external high accuracy simulation was something like 10 to the minus 6, so it was very accurate. And so before I conclude, I just wanted to say that the way I presented this method, it's, we have this clever data structure and a few optimizations, and it works. But in practice, there's a dozen things that broke along the way before we could analyze it. So I did want to acknowledge those, the engineering effort that sort of went into this. So sort of in conclusion, the talk is about linear time invariant systems, and it's sort of an exciting result because it's 2 orders of magnitude more in terms of the number of dimensions. The reason why you want these large systems, a lot of times the large models will come from things like swarm robotics, maybe circuit designs, or even partial differential equations. So in the future, we'll look at sort of bigger systems. And so the tool's available, the source is available, so please download it and give me feedback. Thank you.
Questions? So, Stan, what are the challenges in extending this to the hybrid setting?
So we have a version of HYLA that works in the hybrid setting without inputs. The challenge with inputs is that the way a generalized star set is designed, you need to be able to know, you need to be able to insert constraints into it when there's, for example, an invariant is violated or you reach a guard. And doing that on the current setup doesn't work when you have this Minkowski sum. So we need a better data structure, which we're working on a little bit as well.
Thanks.
So
Other questions?
very interesting work. You had also a nice motivation there, but there you had nonlinear dynamics.
Mm-hmm.
So what's your road towards also achieving nonlinear dynamics with this approach?
Yep, so the way nonlinear dynamics are usually handled is a process called hybridization. And so what that's sort of the intuition behind that is a nonlinear function is really just a piecewise linear function with some noise, right? And so the piecewise linear part would be the linear part, and the noise would be the inputs. So it's possible you can do this sort of piecewise linearization on trajectories and then use it for nonlinear systems. We haven't done that yet, but that's what I'm thinking.
Great. All right. Let's thank Stan again.